So we just learned about the Newton's law of universal gravitation, and we will check how that works out at the Earth's surface. So that is the Newton's law right here. F sub g equals g times m1 m2 over r squared. On the Earth's surface, m1 becomes a mass of the first object, or I'm going to say m. The second one, that is the mass of the Earth, and then the radius between the objects becomes the radius of the Earth, which is known, and it is 6.38 times 10 to the power 6 meters. So we also know that the um, force of gravity due to the Earth is mg, and it has to be equal g times me, right? We plug in over re squared. Well, we can see that masses cancel out, and therefore the acceleration of gravity on the Earth's surface has to be equal g mass of the Earth over the square of the radius of the Earth. So notice how the acceleration of gravity, the lowercase g and the capital G, the constant, they are not the same. They are related, however, by this equation. So they're connected. Now, until this g was measured, people did not know what the mass of the Earth is. But after Cavendish measured g, and people knew this coefficient, they were able to measure me, calculate mass of the Earth like this. So we can multiply both sides by r squared and divide by g. So then mass of the Earth will have to be equal lowercase g times radius of the Earth squared over capital G. Now let's plug in the values that we know. We know 9.8 meters per second squared for G. Radius of the Earth, we just said, it's 638 times 10 to the power 6 meters, and it has to be squared. And then we divide by the constant, 667 times 10 to the negative 11, that's 11, and it's supposed to be Newton times meter squared over kilogram squared. Those are the units. So now if you look at the units, they are going to cancel out, and we will get 5.98 times 10 to the power 24 kilograms. All right, so then this equation can be applied. This equation can be applied to all the other planets, and we can calculate the masses of other planets. And GM and R would refer to those planets, right? GM and R. And now we're going to look at an example. In this example, we will calculate gravity on Mount Everest, which is very high. It is 8,850 meters above sea level. We will calculate the value of g on top of that mountain. In other words, what is the acceleration due to gravity of objects allowed to fall freely at this altitude. And we will ignore the mass of the mountain itself. So we know that so in our equation, we're going to use g equals, lowercase g is going to be equals g, and then we will use mass of Earth over r squared. Okay, now r squared is actually not going to be just the radius of the Earth, right? Because it's above the Earth's surface. So r is now going to be the radius of the Earth, which is 6,380 kilometers, plus, if we convert this into kilometers, we will get 8.9-ish, right, if we round. So that's going to give us 6,389 kilometers, or we can say it is 6.389. This is 6 times 10 to the power 6 meters. Okay, now let's plug into our equation, and then we're going to get that g has to be equal 6.67 times 10 to the power negative 11 Newton meters squared over kilogram squared, multiplied by the mass of the Earth, 598 times 10 to the power 24 kilograms. This is 24 all over, and then the radius is 6.389 times 10 to the power 6 meters. Now, once we simplify everything, we're going to get 9.77 meters per second squared, which means it's a reduction of 3 parts in 1,000. So it's about 0.3%. So the acceleration is actually less. The objects will fall slower at the top of the mountain. And now let's take a look at a table. In this table, we can look at acceleration due to gravity at various locations, and we can see that they are slightly different. Now, why is it so? Because we know that Earth is not a perfect square. It's squished on the top and the bottom, right? It bulges at the equator. Also, it has the mountains, it has the valleys, so it is not the perfect object which we use for our physics purposes. And another thing is that the mass of the Earth is not distributed uniformly as well. So because of that, we have different acceleration in different places, but we assume that it's 9.8 meters per second square, and we write the weight of an object as mg.